Okay, class, we're going to do example number 4, and we are going to work on summation notation. So what we need to do is, for this series, where we have 4, 8, 12, all the way up to 100, we have to see what the pattern is. And I can see that I'm adding 4, and if I continue adding this pattern, we're going to keep adding 4. And another way of thinking of this is these are all multiples of 4. We have 4 times 1, 4 times 2, 4 times 3, 4 times 25. So when you have multiples of a number, it's always going to be 4n because they're multiples of 4. Okay, so the notation, we are going to use the sigma notation. We're going to sum up my multiples of 4, my 4n's, and I'm going to start by plugging in n equals 1, because when I plug 1 into my pattern, I get 4 out, 1 times 4. When I plug 2 in, I get 8 out, which is my second term. When I plug in 3, I get 12, which is my third term. I'm going to keep plugging in numbers, 1, 2, 3, 4, all the way up until, what do I have to plug in to 4n to get 100? Well, that would be 25, because 4 times 25 is 100. So this would be the sigma notation for this series. Okay, same idea here for the second problem. Whenever we have our series or our sequence in fractions, you should write the first term kind of in fraction. And I'm going to look at the fractions separately. So I notice on the top it's 2, 3, 4, 5. It's increasing by 1. Okay, I keep adding 1. And on the bottom, I have my first term is 1 squared. My second term is 2 squared. 3 squared and 4 squared. You should be able to recognize the perfect squares. So my pattern is, I have on the bottom, for the first term I have 1 squared, second term is 2 squared. It's whatever my term number is, and then I'm squaring it. And on the top, well, the first term is 2, and the second term is 3, and the third term is 4. So the top number is 1 more than the term number. It's my term, n plus 1. So for sigma notation, you're going to sum up your pattern, n plus 1 over n squared. And I'm going to start when I plug in 1. Now let's check. Plug in 1 to the top, you get 2, which is what I want. Plug in 1 to the bottom, you get 1 squared, which is 1. Good. Plug in 2, you get 3 on the top over 4, which is what we wanted. Plug in 3, get 4 on the top, 9 on the bottom. Good. We're going to keep doing this pattern all the way out. Well, it's an infinite series, so we're going to go to infinity, and that would be our sigma notation for our infinite series here. Okay, so now we're going to kind of use our notation and calculate the sum. So we are going to sum up k squared plus 1, starting with k equals 5 up until k equals 8. So if we expand this out, we're going to plug in 5. So you get 5 squared plus 1. Okay, so that's when we plug in k equals 5. And then sigma means sum, so we're going to add up to it when we plug in k equals 6. When we plug in 6, we get 6 squared plus 1 plus k equals 7, 7 squared plus 1 plus k equals 8, we get 8 squared plus 1. Okay, so when we plug this in into our calculator, you get 25 plus 1 is 26, plus 37, plus 50, plus 65. So you just plug those numbers into your calculator and you get 26 plus 37 plus 50 plus 65, that is 178. Which tells me that the sum of this is 170. Okay, so now what we're going to do, we're going to go over factorial. So as a quick reminder, if you have 3 factorial, it said factorial, this is 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. whatever number factorial, it means keep multiplying by the whole numbers all the way down till you get to 1. And then you would multiply those numbers out and you'd get 6. And here you get 5 times 4 times 3 times 2, which is 20, times 6, or 120. Okay, so here we're going to simplify the factorial. So 10 factorial is 10, 9, 8, 7, 6, all the way down to 1. Okay, 3 factorial is 3, 2, 1. All over 4 factorial is 4 times 3 times 2 times 1. 6 factorial is 6, 5, all the way down to 1. And since all these numbers are just being multiplied, you can cancel. So showing what cancels off. 6, remember 10 factorial had this 6 all the way down to 1, which is 6 factorial, 6, 5, 4, 3, 2, 1. And on the bottom we had 6 factorial, which was 6, 5, 4, 3, 2, 1. Okay, here we have 3 times 2 times 1, which cancels with 3 times 2 times 1. And 4 goes into 8 2 times. So we've canceled everything on the bottom, and what we have left on the top is a 2, a 10, a 9, and a 7. So when we multiply those numbers together, we get 1260. So this number right here is 1260. And there is a way to do this on your calculator, but for now, you need to know how to simplify these without a calculator. Okay, so here we're going to write a rule for the number of oranges in each layer. Okay, so we have our diagram, and we have, oops, excuse me, there's the wrong button. We have our first row, there's 1 orange. And then in our second row, we have a 2 by 2 square, so we have 4. And then in our third row, we have 3 by 3 square, 3 by 3 square, or 9, and so on. For the fourth row, we have a 4 by 4 square, or 4 squared. So if we see a pattern and we want to write a rule for the number of oranges, the number of oranges is a sub n. What's the rule? The first term had 1 squared. The second term had 2 squared. The third term had 3 squared. The fourth term had 4 squared, so it's just n squared. So that would be our nth term rule. Okay, well that is all, and I will see you in class. Have a lovely evening.